So analysis of the titration curve. Suppose we have M in the beaker and L in the burette. After the addition of L, before the equivalence, so the L added will disappear completely. The concentration of M will decrease, so the concentration of ML increase. Before equivalence, L added is limiting. So if we want to calculate the concentration of L before equivalence, L is found as traces. The concentration of M decrease and the concentration of ML increase. So after each addition, we have to calculate the M in the solution, the concentration of L in the solution, and the concentration of ML in the solution. When we calculate M in the solution, we calculate PM. And when calculate L in the solution, we calculate PL. So we can study the variation of PM as a function of the volume added, or PL as a function of the volume added. It depends on the request in the exercise. At V equals 0, as I said, we have 4 characteristic points. The V equals 0, the V equivalence over 2, the V equivalence, after equivalence. I will start for addition V equal 0, يعني before addition of the ligand L. Before addition of the ligand L in the solution, we have only M. And the concentration of M in the solution is equal to C0. So what is PM? PM equal minus log M in the solution. So PM equal minus log C0. So PM equal PC0. This is the PM at the starting before addition of L. For a volume between 0 and V equivalence, or in other words, the addition of the ligand L, all quantity of the ligand L disappear, so we'll have traces of L, or we can say M is in excess. So what would happen when we add ligand at a volume between 0 and VE? We have a reaction between M and L in the direction of formation of ML. At T equals 0, I prefer to start the table of conversion according to the number of mole. And when they ask to calculate the concentrations at any addition, I can divide by V total. So at T equals 0 initially, we have N0. The ligand added for a volume between 0 and VE, I will suppose that I add NL, the number of mole of ligands. At T equals 0, we don't have ML, so 0. The reaction will proceed till T equal infinity. Why till T equal infinity? Since this is a titration reaction. So this is at T equals 0. The reaction will proceed till T equal infinity. So L is limiting since the volume added is before V equivalence. Okay. So the quantity of M remained. 1M will react with 1L. So NL react completely. The number of moles of M remained at T equal infinity is N0 minus L. The quantity of L is practically 0 since L is limiting, and ML4 is equal to NL. Therefore, the reaction will proceed backward. So NL will be NL minus epsilon, L will be epsilon, and M will be N0 minus NL plus epsilon. Pay attention that this reaction, M plus L, is complete in direction 1 and is very limited in direction 2. So epsilon is negligible with respect to NL. Here we have only epsilon. I cannot remove this value. And epsilon will be also negligible with respect to N0 minus N. So what is the concentration of M? The objective is to calculate PM. The concentration of M is equal to the number of mole of M in the solution divided by V total. So the concentration of M equal Nm divided by V total. Nm is equal N0 minus NL divided by V total. And N0 equals C0 V0. The number of mole of L, pay attention that the concentration of L is known since we put L in the burette. So is equal to the concentration of L times V divided by V total. So we calculated the concentration of M, then we deduce PM equal minus log Cm equal minus log C0 V0 minus Cl VL divided by V total. Suppose they ask to calculate PM. If the question is to calculate PL, it's very easy. If we want to calculate PL, equal minus log L, concentration, equal minus log epsilon divided by V total. So you have to calculate epsilon. And how to calculate epsilon? Epsilon is calculated from K of the reaction, so from Kf. If we put Kf equal ml divided by m times L, so you can calculate Kf is given, you can calculate epsilon. In the electrochemistry, if you remember, we calculated the potential of the solution after additions of, for example, of oxidant or of reductant to oxidant, it depends. What to do? Before equivalence, we said that it's easier to work on the couple present in the beaker. After equivalence, it's preferred to work on the couple present in the burette. That does not mean we could not work on both couples. I said it's easier to work on the couple present in the beaker if the volume added is before equivalence, and it's preferred to work on the couple present in the burette if the volume is greater than V equivalence. This is the same. In this exercise, since the L added is limiting, that means L will disappear completely. So if they don't mention to work on PL or PM, in this type of exercise, before equivalence, it's preferred to work on the couple, on the species present in the beaker. So in the beaker we have M, it's preferred to work on PM. That does not mean we could not work on PL. If we work on PL, we have to calculate epsilon. After equivalence, M disappear completely and L is excess. So it's preferred after equivalence to work on PL, since L is present in certain amount, is an excess. In the exercise, they will mention to work on PM or PL. In the exercise, they request, for example, to work on PM. In most cases, they request to work on PM. So if the student wants to calculate PL before equivalence, he should pass by the calculation of the epsilon from the value of Kf. Now, the third equivalence, the first characteristic point was V equals 0 before addition of the ligand. The second characteristic point is before equivalence. The third characteristic point is at equivalence. Suppose you add ligand at a certain volume equal VE. What would happen? When L is added to M, it will proceed in the direction of formation of ML. At T equals 0, we have N0, we have NL. This reaction will proceed till T equal infinity. So N0 react completely practically zero, NL react completely practically zero, and N of ML is equal N0 or NL added at VE. Then the reaction will proceed in the backward direction. So N minus epsilon, I noted N, since N0 equal NL added at V equivalence, epsilon, epsilon. N minus epsilon, epsilon is negligible with respect to N, since the reaction is very limited in direction 2. Now we have to calculate PM. PM equal minus log M equal minus log. Pay attention, I work on number of moles, so epsilon is number of mole minus epsilon divided by V total. In this type of exercise at VE, I should pass by the calculation of epsilon. I don't have another solution. I should calculate epsilon. So how to calculate epsilon? We can calculate epsilon by using Kf, which is equal ml times divided by m times L, or by using Kd, which is equal m times L divided by ml at concentration kilon hole. The all concentrations are at equilibrium. So you can work on Kf or on Kd to calculate epsilon. Kd equal m times L divided by ml. Why I use Kd? In the acid base, the characteristic is Ka. In the electrochemistry, the characteristic is E. In the solubility, the characteristic is Ksp. In the complexation, the characteristic is Kd. We proved in the previous sessions that Ka in the acid base is similar to Kd in the complex, and Kb in the acid base is similar to Kf in the complex. So in the complexation, we prefer to work on Kd. Kd equal m times L divided by ml, and these concentrations are at equilibrium. M at equilibrium equal epsilon, L at equilibrium equal epsilon, so M equal L at equilibrium equal M square divided by ml, which is N divided by V total, or I noted C prime 0, implies M square equal Kd C prime 0, so M equal radical Kd C prime 0, so Pm equal half Pkd minus log C prime 0, or equal half Pkd plus P prime C0. Pay attention that C prime 0 at equivalence is different from C0 at T equals 0. Since at T equals 0 we convert all M to ML, so the number of mole of M initial equal the number of mole of ML formed at equivalence. But if we want to calculate the concentration, we have to divide by V total, and V total is equal to VE plus V0 at equivalence. Okay, so Pm equal half Pkd minus log C prime 0. This is the same formula as the pH of weak acid. What is the weak acid? The weak acid is Ha, is donor. What is the analogy in the complex? The analogy on the complex of Ha is Ml. At equivalence, we have only Ml, since the L added convert completely M. So at equivalence, we have only Ml, and Ml is is a donor. So what is the pH of the donor HA is half pKa plus PC0. What is the P particle Pm of the Ml donor is equal half pH HA the analogy is ml, Ka, the analogy is Kd, pH, the analogy is Pm, pH equal half pKd, half pKa plus P prime C0, here half pKd plus PC0 prime. This is the same analogy of the acid base. And the last point is after equivalence. After equivalence, the M is limiting and the L is excess. So at T equals 0, we add. We have initially N0, L is NL added, ML equals 0. The reaction will proceed till T equal infinity. Since the volume added is after V equivalence, that means M is practically 0, NL is excess, so equal NL minus N0, and we have N0. Then the reaction will proceed in direction 2. So we have N0 minus epsilon, NL minus N0 plus epsilon, epsilon is negligible with respect to N0, and epsilon is negligible with respect to NL minus N0, since the reaction is very limited in direction 2, and we have epsilon. So to calculate PM, we have to pass by the calculation of epsilon. In the final solution, we have ML, N0, we have L, NL minus N0, and we have M traces as epsilon. We can apply the analogy of Henderson formula, Pm equal pKd plus log L divided by ml. This formula can be applied independent of the exercise. So Pm equal pKd plus log L. What is L? Is NL minus N0 divided by V total divided by ml, which is at equilibrium, which is N0 divided by V total. We cancel V total, so we obtain pKd equal pKd plus log NL minus N0 divided by N0. So Pm equal pKd plus log CLV added minus C0 V0 divided by C0 V0. And we obtain the following curve. At T equals 0, what are the species present? Here we have M. When we add L, M will decrease. So at equivalence, we have ML. After equivalence, we have ML plus L. Okay? Between this point and ML, we have M plus ML. So this is the domains of predominance. Look, when the volume V added, so the percent of M decrease and the percent of ML increase. This is ML percent. And this is M percent. M percent decrease till V equivalence. At equivalence, the percent of M is 0. ML increase from T equals 0 till the equivalence, and at equivalence is equal to 100%. And we have several characteristic points. What is PM at the beginning? We prove the relation PM at the beginning equal PC0. What is PM at equivalence? PM at equivalence equal half pKd plus, pay attention, P prime C0, and C prime 0 is different from C0. Okay, C prime 0 equal N0 divided by V total, which is V0 plus VE, but C0 is equal N0 divided by V0. So at equivalence, all M has been transformed to ML as number of moles, but the concentrations are different. So this is the titration curve of the complexation.